We have seen the case of a charge, electrical charge moving along a path and trying to work the expressions and understand the fields radiated by this charge. To complete the picture, we are now going to consider the magnetic case. And for this purpose, we first have to comment on the simplest way to produce fields, magnetic fields. And there are two very well known. One is a magnet. The magnet has poles, and from pole to pole there's a magnetic field. The other way is to have currents moving along a wire. And in this case, we also have magnetic fields that go around the wire. It was well known that if we approach a magnet to a wire, or if we have a wire like this and a second wire with another current, then forces will be applied. And the currents, in some way, will be trying either to approach or repel. In exactly the same way the charges did. This is just the first basic factor. Those forces, in this case, behave with a little bit different law, because they depend not only on the amount of charge, but also on the velocity the charge is moving. So we have here the product of the charge times the velocity. And the force is different, because it will not follow directly the field, the magnetic field. In fact, the force will be orthogonal, will be perpendicular to the velocity and the magnetic field. And this is why we have here the cross product, the vector product. So we have a force which is different to the ones we had before. When both electric and magnetic fields are present, this is the general law that will give you the force on a charge. It will be directly proportional to the electric field, plus a second force that will be exerted by the magnetic field, and in this case, it will be also dependent on the velocity of the charge. This is just the basic law. It's normally denoted in honor of Lorentz with this name. This is the Lorentz force law, and it's a fundamental law of electromagnetics. We are going to consider a simple but interesting case, and you will see why in a few moments. It's just a charge Q, and now since there is motion, there's velocity, we also need to know the mass of this charge. So here we have the charge and the mass, Q and M. And we add in green here the magnetic field. And we have to represent this field. In this case, we represent this field by dots. And those dots mean that the magnetic field is coming out of the screen, is pointing from the screen towards you. So the charge is moving on the screen plane, and the magnetic field is perpendicular. So this cross product will give you a force in this direction. This is a central force, if you want. It's pointing towards the center. When we have this situation, what happens is, as the charge moves, this force just pulls the charge towards here. So the charge, instead of moving like this is uniform motion. This is constant velocity. There's no acceleration. The charge is moving in this direction, is trying to move in this direction, but this force will really bring it and make it follow a circular path. This is exactly what happens in the case of our satellites. When we launch a satellite, the attraction force will just make the satellite go through an orbit. And this is why the moon is orbiting around the Earth on a circular path. And the radius of this orbit is r, and we're going to find its value. It's a simple problem because, first of all, we have an electromagnetic force, magnetic force in this case. Since there's no electric field, to simplify things, we only have the magnetic case. this is just the cross product, and we have make this drawing in a careful way to make them orthogonal. So we just have this force, which is proportional to the charge, the velocity, and the magnetic field, and is pointing towards this. This is the unit vector r, that instead of going in this way, is just pointing towards the center. And this is the force. But also this is the centrifugal force that will try to pull away the charge, and this is proportional to the mass of the charge and the radial acceleration. And you know also from elementary physics that this is proportional to the square of the velocity divided by the radius. And in equilibrium, those two forces will just compensate one another. And this is just the law that will give you the path, will give you the radius in function of all those parameters. You see there's a velocity here, there's the square of the velocity there. So now we have just the general law for the orbit. The radius of the orbit is proportional to the mass and the velocity, and inversely proportional to the charge and the magnetic field. This is an important feature because it means that if we have, let's say, ions of equal charge injected, in this case here, moving with the same velocity but have different masses, what will happen? That they will all describe different circles. The radius will be different. Those with a larger mass will go on the outer paths. Those with lower mass will go in inner paths. And this was very useful when it was really discovered, just to separate different ions or different atoms depending on their mass. And this was one of the first procedures to separate isotopes in radioactive materials. The momentum is just the mass times the velocity, so we have this second expression for the mechanical momentum. And an important parameter is the time it takes for the charge just to go a full circle around, one revolution, if you want. The period is the length, 2 pi r, divided by the velocity. This is uniform motion, once again. And you see that this period is equal to 2 pi, the mass, the charge, and the magnetic field. And if you look at this and compare with this, you will see that there is something missing. What? The velocity. It means that no matter what the velocity is, although the radius of the orbit may be different, they all go along in the same time, in the same period. So it will take exactly the same time to go around if the circle was large than if the circle radius was small. So the period is independent of the mass, is independent of the velocity of the charge. Certainly it's dependent on the mass, the field, and the charge. If we know the period, we also know the angular velocity, and this is the value for it. So, in a simple way, if we increase the velocity, we will increase the radius of the orbit, but we will be maintaining the period constant. But there's a problem. If we increase the velocity a lot and we approach the velocity of light, the problem here is that the mass will not be constant. The mass will be increasing as the velocity approaches the velocity of light. And in this case, if the mass increases, then the period also changes. So this is an important parameter to consider, how the velocity of the charge may be approaching the velocity of light. As an example, for a magnetic field of 1 Tesla, in the case of the electron, this frequency, this angular frequency, which normally is called the cyclotron frequency, is 28 gigahertz. It falls into the realm of the microwaves. Here is just a simple picture of the original ideas of the cyclotron. The cyclotron was conceived by Lorentz in the late 20s. That won him the Nobel Prize and was heavily used during the Second War by the Americans. Here you have the two magnets that will produce the magnetic field. And in between the magnets, we have here a sandwich of two metallic plates. They are called Ds because they look like a D. They have the shape of the D. But this is like two parallel plates and an outer cylinder here. And the electrons, the charges, the ions are moving inside in orbits. If you look at the orbits drawn here, you will see that they are not circular. They are circular in certain paths, and then once again, but you see the radius is larger. It looks like a spiral. What happens here? The idea is that to inject a charge, it goes around, and when it reaches this point, since this is metallic, then we have another voltage difference here that will accelerate the charge from here to here. So the velocity will increase as it goes through the gap. So now it will describe a larger orbit. And again, and again, and again. And this is just the simple drawing you have here. It goes along this path, and at each crossing, the voltage, which is just this waveform, keeps accelerating the charge until it has enough velocity to be launched away. This is a very clever scheme, and what it makes it possible is the fact that the period is independent of the velocity. So although here the velocity is larger and larger, you can synchronize this waveform with the charge and have just something that keeps pushing the charge along this path, increasing constantly its velocity. And this is a very compact accelerator compared to the linear ones in which you do this process but along a line. And this is what makes cyclotrons so important.